So this is an article by Andreessen Horowitz. I found it to be really interesting. It's the emerging architectures for LLM applications. So let's start. Large language models are a powerful new primitive for building software. But since they are so new and behave so differently from normal computing resources, it's not always obvious how to use them. In this post, we are sharing a reference architecture for the emerging LLM app stack. It shows the common systems, tools, and design patterns we've seen used by AI startups and sophisticated tech companies. This stack is still very early and may change substantially as the underlying technology advances. But we hope it'll be useful reference for developers working with LLMs now. This work is based on conversations with AI startup founders and engineers, with a whole bunch of smart people. So thank you for your help. So it's important to call out names, they've done the work. So this is our current view of the LLM app stack. And so they have the contextual data coming in, they have the standard data engineering pipeline, Databricks, Airflow, unstructured data, maybe from S3, stuff like that. They go to the embedding model, and then they would probably generate these embeddings. They have called out OpenAI, Cohere, Hugging Face. I think Hugging Face is, maybe sentence transformers, I guess. And then they go to the vector database, Pinecone, VV8, Chroma, pgvector. I personally like Quadrant. There's also Milvus, I think a bunch of them, but yeah, you can't put all of them in there. So, and then they go to the orchestration layer, and you have Python, DIY, Langchain, Llama Index, ChatGPT. Yeah, so I guess you have Langchain, Llama Index, and Chat. Yeah, this is like a very confusing set of technologies here. One is a language, or I guess you can do it yourself with Python, or you can use Langchain, which is in Python or JavaScript, and then you have Llama Index, and ultimately they're going to call out to an API that's here, right? And I think that would be here. But yeah, let's read through and figure out. And then you have the few short examples. They have playgrounds. I guess this is where they want ChatGPT here, I suppose, which is sort of like a playground, and they have nat.dev, human loop, and then I guess this is the tooling layer where you're going to call out to different APIs and plugins, and they have SERP, which is essentially like a search API. You have Zapier, which basically integrates with everything else, and I guess they also threw in Wolfram here for knowledge queries and things like that. Yeah, and I think this is the interesting part, right? So once it goes through the Langchain layer, then they also have an LLM cache. I would like to know about it. But then they also have Redis, SQLite, and they have the more specialized sort of like GPT cache. It is still going to use like vector embeddings and then try to find out if the question is similar, then answer with a stored response and so on and so forth. And then they have the logging and LLM ops. They have MLflow, prompt layer, Helicon, and also weights and biases. Again, a bunch of different technologies here, but let's read through. I think they are also going to explain each one of them in detail. So yeah, here is a list of each project for quick reference. They have so they have Databricks, Airflow, unstructured, OpenAI, Cohere, Pinecone, VV8, a whole bunch of these. There are many different ways to build with LLMs, including training models from scratch, fine-tuning open source models, or using hosted APIs. The stack we are showing here is based on in-context learning, which is the design pattern we have seen in the majority of developers start with, and is only possible now with foundation models. In the next section, it gives a brief explanation for this pattern. Experienced LLM developers can skip this section. Design pattern, in-context learning. The core idea of in-context learning is to use LLMs off the shelf without any fine-tuning, then control their behavior through clever prompting and conditioning on private contextual data. For example, say you're building a chatbot to answer questions about a set of legal documents. Taking a naive approach, you could paste all the documents into a ChatGPT or ChatGPT-4 prompt, then ask a question about them in the end. Well, the problem is context length, right? So you don't have infinite context window. So this may work for very small data sets, but doesn't scale. The biggest GPT-4 model can only process about 50 pages of input text, and performance measured by inference time and accuracy degrades badly as you approach this limit, called a context window. Yep. In-context learning solves this problem with a clever trick. Instead of sending all the documents with each LLM prompt, it sends only a handful of most relevant documents. And most of the relevant documents are determined with the help of, you guessed it, LLMs. Yeah, we'll come to this because I guess there is some sort of embedding that's going on, and technically embedding is a large language model, but not in the same way that ChatGPT is, which is RLHF based things, and that's what most people think LLMs are. But yeah, we'll get to that. At a very high level, workflow can be divided into three stages: data processing or embedding. This stage involves storing private data, legal documents in our example, to be retrieved later. Typically, these documents are broken into chunks, passed through an embedding model, and then stored in a specialized database called a vector database. Prompt construction or retrieval. When a user submits a query, a legal question in this case, the application constructs a series of prompts to submit to the language model. A compiled prompt typically combines prompt template hard-coded by the developer, examples of valid outputs called few short examples, any necessary information retrieved from the external APIs, a set of relevant documents retrieved from the vector database. Prompt execution or inference. Once the prompts have been compiled, they're submitted to a pre-trained LLM for inference, including both proprietary model APIs and open source or self-trained models. Some developers also add operation systems like logging, caching, and validation at this stage. Yeah, sort of makes sense. This looks like a lot of work, but it's usually easier than the alternative, fine training or fine-tuning the LLM itself. Again, I mean, fine-tuning is done for a different reason. They're kind of like orthogonal techniques. I don't think prompt engineering can be replaced with fine-tuning, or fine-tuning can replace prompt engineering. I mean, there is some overlap, of course, but it's fundamentally different. So you don't need a specialized team of ML engineers to do in-context learning. You also don't need to host your own infrastructure or buy an expensive dedicated instance from OpenAI. This pattern effectively reduces the AI problem to a data engineering problem that most startups and big companies already know how to solve. This also tends to outperform fine-tuning for relatively small datasets, since a specific piece of information needs to occur at least 10 times in a training set before an LLM will remember it through the fine-tuning and can incorporate new data in near real time. Yeah, I mean, I've always maintained that if you want to change the style of the output, that's where fine-tuning would help. Like, for example, RLHF is a clear example, because instead of just being a word predictor, you wanted to turn it into a question answering sort of like a format, and to change the way in which it answers, right? The style of the answer. I think that's where fine-tuning helps. But yeah, and fine-tuning also gives it knowledge, but the context has a lot more weightage in terms of knowledge than fine-tuning. This makes sense. One of the biggest questions around in-context learning is, what happens if we just change the underlying model to increase the context window? This is indeed possible and is an active area of research. See the Hyena paper in this recent post. But this comes with a number of trade-offs. Primarily, the cost and time of inference scale quadratically the length of the prompt. Today, even linear scaling, the best theoretical outcome, would be cost prohibitive for many applications. A single GPT-4 query over 10,000 pages would cost hundreds of dollars at the current API rates. So we don't expect wholesale changes to the stack based on the expanded context windows, but we'll comment on this more on the body of the post. All right. So yeah, this is good. Also, there is this really interesting class of models called RWKV models that are essentially RNNs, but you train them as transformers, but on inference they act as RNNs. I mean, again, it's an area of research at this point. I mean, there's no RLHF kind of models, so they are essentially stochastic parrots at this point. But that'll be interesting to see what happens if those kind of models come in. But we'll see. If you'd like to go deeper on in-context learning, there are a number of great resources. The AI Canon, especially the practical guides to building with LLM section. The remainder of this post will talk about the reference stack using workflow above as a guide. Yeah, I think we should do this on a future video, the AI Canon. But yeah, let's continue. So for each one of these sections like this, they're gonna delve into it. So the first is data processing or embedding. So you get the contextual data, you have the existing data pipelines, you then generate the embeddings, you store them into vector database, and then somehow have an API layer have an ability to work with the vector database, I guess. So let's see. Contextual data for LLM apps include text documents, PDFs, and even structured formats such as CSV or SQL tables. Data loading and transformation solutions for this data can vary across developers we spoke with. Most use traditional ETL tools like Databricks or Airflow. Some of Some also use document loaders built into orchestration frameworks like Langchain, powered by Unstructured, and Llama Index, powered by Llama Hemp. We believe that this piece of stack is relatively underdeveloped, though there is an opportunity for data replication solutions purpose built for LLM apps. And I think this is really important because and most document loaders in Langchain cut it at 1,000 word limit, and it breaks it right in the middle of a sentence, and then it creates an embedding on that. I don't think that's a good idea. When we built Kili, we built our own sentence tokenizer, so to speak, so that we can create embeddings with sentence transformers. I think there's a lot more to be done here on how do you generate embeddings for these kind of documents, right? So for embeddings, most developers use the OpenAI API, specifically with the text embedding ADA 002 model. It's easy to use, especially if you've used in other OpenAI APIs. It gives reasonably good results and is becoming increasingly cheap. Some larger enterprises are also exploring Cohere, which focuses their product efforts more narrowly on embeddings and has better performance in certain scenarios. For developers who prefer open source, Sentence Transformers library from Hugging Face is a standard. It's also possible to create different types of embeddings tailored for different use cases. This is a niche practice today, but promising area of research. Yeah, I mean, for embeddings, I feel, what matters is performance. If you're going to ingest like tons and tons of documents, and they all have to go through the embedding pipeline, which is essentially a GPU enabled model, right? You want to make sure that they go through and generate through all those layers to generate that embedding. That is going to be a bottleneck. So you want something that would either be hosted. For Vivery, we are just using OpenAI API with exactly text embedding ADA 002, but we could easily be using SBERT, which is what is sentence transformers, and use different models for that. The most important piece of the pre-processing pipeline from a system standpoint is a vector database. It's responsible for efficiently storing, comparing, and retrieving up to billions of embeddings. Example, that is vectors. The most common choice we have seen is in the market is Pinecone. It's default because it's fully cloud hosted. So it's easy to get started with and has many of the features large enterprises need in production. Example, good performance at scale, SSO, uptime, SLAs, etc. My personal favorite here is Quadrant, QDRANT. Quadrant is written in Rust, and I really like it. It's actually very, very simple. It's easy to get started, and I feel there's also this other one which is called Milvus. Milvus has its API layer written in Go, but the core engine is still written in Rust. And both Milvus and Quadrant implement HNSW, which is the hierarchical navigable small worlds algorithm, which is extremely efficient, quickly narrow down on the set of vectors that you need. So there is a huge range of vector databases available, notably open source systems, VV8, Vespa, Quadrant, Quadrant they call it. They generally give an excellent single node performance and can be tailored for specific applications. So they are popular with experienced AI teams who prefer to build bespoke platforms. Local vector management libraries like Chroma and Face, which is Face is, I think, Facebook AI's similarity search. They have great developer experience and are easy to spin up for small apps and dev experiments. They don't necessarily substitute for a full database at scale. That's true. OLTP extensions like pgvector. I don't know how I feel about this. For devs who see every database shaped hole and try to insert Postgres, or enterprises who buy most of their data infrastructure from a single cloud provider, this is a good solution. Ouch, for vector support. It is not clear in the long run if it makes sense to tightly couple a vector and scalar workloads. There is a case for having the data side by side, the same as like full text search sort of thing. It's just a different index on your main data, because you can look at it in two different ways. You can think of the embeddings as a data, or you can think of embeddings as a sort of like an index format, and then which then points to the actual data. And I feel you should think of embeddings as an index format rather than embeddings as data. So in that sense, I feel pgvector is a good solution. But then most people would be using something like AWS RDS and things like that. It's not trivial to get pgvector installed onto that and then also perform well. I think it will take a long time before something like pgvector gains mass adoption. On the other hand, things like Quadrant or Milvus probably will get adopted, and I feel AWS may just include a vector store. They probably have, I don't know, but yeah, they may just have a vector database as a part of their offering. Looking ahead, most of the open source vector database companies are developing cloud offerings. Our research suggests achieving strong performance on cloud across a broad design space of possible use cases is a very hard problem. Therefore, the option set may not change massively in the near term, but it likely will change in the long term. The key question is whether vector databases will resemble their OLTP and OLAP counterparts, consolidating around one or two popular systems. Vector databases are relatively simple beasts when compared with OLTP and OLAP kind of like counterparts. And I think it's just one part of the puzzle. You would still want to augment the results that you get from vector databases with also results from traditional search platforms, because if you have clear search terms that give you better results at a fraction of the cost, why would you not do that, right? Another open question is how embeddings and vector databases will evolve as the usable context window grows for most models. It's tempting to say embeddings will become less relevant because contextual data can just be dropped in on the prompt directly. However, feedback from experts on this topic suggests the opposite, that the embedding pipeline may become more important over time. Large context windows are a powerful tool, but they also entail significant computational costs. So making efficient use of it becomes a priority. We may start seeing different types of embedding models become popular, trained directly for model relevancy, and vector databases designed to enable and take advantage of this. There is something to it. I think OpenAI embeddings has like 1536 dimensions. I think 512 into 3, I guess. Sentence transformers have, depending on the model you choose, you could have something from 512 to 768 dimensions. And again, the context windows is not infinite. I mean, as it was noted earlier in the blog post, that searching through the context window is essentially quadratic time. Depending on the model that you choose, if it's a 4K context window or a 32K context window, you are essentially paying the price for every token that gets generated because you have the attention window that's there. Having a good vector embedding database and working with a smaller context window, if you can make that work and have those embeddings be very relevant to the kind of query that you want, it will pay off in the long run. So let's look at prompt construction and retrieval, or string templating mostly, right? So strategies for prompting LLMs and incorporating contextual data are becoming increasingly complex and increasingly important as a source of product differentiation. Most developers start new projects by experimenting with simple prompts consisting of direct instructions, zero-shot prompting, or possibly some example outputs, few-shot prompting. These prompts often give good results but fail short of accuracy levels required for production deployments. The next level of prompting jujutsu is designed to ground model responses in some source of truth and provide external context the model wasn't trained on. The Prompt Engineering Guide catalogs no fewer than 12 more advanced prompting strategies, including chain of thought, self-consistency, generated knowledge, tree of thoughts, directional stimulus, and many others. These strategies can also be used in conjunction to support different LLM use cases like document question answering, chatbots, etc. And yeah, I mean, when I read the Prompt Engineering Guide and I was playing around with prompts, I feel prompt engineering, it's its own thing. Earlier, I used to talk of it derisively, almost like dismissing it, thinking that prompt engineering is not that great. It's just you expressing your ideas in different ways. It's not real engineering. But I mean, there is something to how you instruct these LLMs. It's almost like a horse whisperer sort of thing. So it's a stochastic parrot whisperer, so to speak. There'll be more people who will be naturally drawn towards prompt engineering, and I think it would become its own kind of like a specialty. This is where orchestration frameworks like Langchain and Llama Index shine. They abstract away many details of prompt chaining, interfacing with external APIs, including determining when an API call is needed, retrieving contextual data from vector databases, and maintaining memory across multiple LLM calls. They also provide templates for many of the common applications mentioned above. Their output is a prompt or a series of prompts to submit to a language model. These frameworks are widely used among hobbyists and startups looking to get an app off the ground. with Langchain as the leader. Yeah, I mean, this is 100%. For Vivery, I'm a huge fan of Rust, so I'll be using LLM chain, and filling the gaps as we go along. But yeah, it's very similar technique that I'm going to use. Langchain is a relatively new project, currently on version 0.0.2.1, but we've already started seeing apps built with it moving into production. Some developers, especially early adopters of LLMs, prefer to switch to raw Python in production to eliminate an added dependency. But we expect this DIY approach to decline over time for most use cases in a similar way to traditional web app stack. That's true too. I mean, I guess you will have more such frameworks like Langchain or competitors to Langchain coming up. And it's not a difficult idea. I mean, there is a relatively low technical complexity in Langchain when compared with, say, a traditional web application framework, which has a lot more concerns, how to handle request responses, body streaming, so on and so forth. And compared to that, Langchain is relatively low in technical complexity. So sharp-eyed readers will notice a seemingly weird entry in the orchestration box, ChatGPT. Yeah, in its normal incarnation, ChatGPT is an app, not a developer tool, but it can also be accessed as an API. And if you squint, it performs some of the featured functions such as an orchestration framework, such as abstracting away the need for bespoke prompts, maintaining state and retrieval via contextual data via plugins, APIs, and other sources. Okay, that's why they put this in here. Okay, I can give them that. While not a direct competitor to other tools listed here, ChatGPT can be considered a suitable substitute or a substitute solution, and it may eventually become a viable, simple alternative to prompt construction. Yes, quite true, quite true. I can see that. All right, so now let's go to the prompt execution or the inference layer. So in today, OpenAI is a leader among language models. Nearly every developer we spoke with starts new LLM apps using the OpenAI API, usually with GPT-4 or GPT-4 32K model. This gives the best case scenario for app performance and is easy to use in that it operates on a wide range of input domains and usually requires no fine-tuning or self-hosting. When projects go into production and start to scale, a broader set of options come into play. Some of these common ones we heard include switching to GPT 3.5 Turbo. It's about 50 times cheaper and significantly faster than GPT-4. Many apps don't need GPT-4 level of accuracy but do require low latency inference and cost-effective support for free users. Yes, for Vivery.dev, we would be you would be providing the OpenAI key on this, and you would obviously get a choice on which model that you want to use. And they are right, GPT 3.5 Turbo is quite effective for many of the use cases. Like, for example, if you want to decide on which tool to use, you can use GPT 3.5 Turbo, and you don't need GPT-4 for that. Or for example, extracting structured data from unstructured text. I think GPT 3.5 Turbo does a pretty good job of that as well. You don't need to use GPT-4. But for generating outputs, I would still use GPT-4. And the GPT-4 32K model is only when you are pushing against the 4K limit on the token, and 4K is a lot of tokens. Like when you're pushing against that limit, will kind of like suggest for some prompt templates to automatically switch between GPT-4 to GPT-4 32K depending on the size of the prompt input. Anyway, so experimenting with other proprietary vendors, especially Anthropic's Claude models. Claude offers a fast inference GPT 3.5 level of accuracy, more customization options for large customers, and up to 100K context window. Though we have found accuracy degrades with the length of the input. Yeah, and I think it was also a research paper that I read on, so even if you use rope or you use different kind of techniques to increase the context window, there's a lot more attention that is paid on the beginning of the text or the end of the text. The middle part of the text is often ignored and there is no attention paid to it. So there's a clear case of diminishing returns. I don't know if you can efficiently scale beyond 32K to do this. Yeah, but I mean, it's still early. There's a lot of change happening in this space, so I guess we have to see. triaging some requests to open source models. This can be effective, especially effective in high volume B2C use cases like search or chat, where there is a wide variance in query complexity and a need to serve free users cheaply. This usually makes most sense in conjunction with fine-tuning open source based models. We don't go deep onto that tooling stack in this article, but platforms like Databricks, Anyscale, Mosaic, Model, and Runpod are used by a growing number of engineering teams. Yeah, and we have seen this as well. I think, especially for like calling out different APIs and things like that, and a variety of inference options are available for open source models, including simple API interfaces from Hugging Face and Replicate, raw compute resources from major cloud providers, and more opinionated cloud offerings from those listed above. Right? Um, Open source models trail proprietary offerings right now, but the gap is starting to close. Yeah, with Llama 2, I think this is there. The Llama models from Meta set a new bar for open source accuracy and kicked off a flurry of variants. Since Llama 2 was licensed for research use only, a number of new providers have stepped in to train alternative based models. Together, Mosaic, Falcon, Mistral. Meta is also debating a truly open source release of Llama 2, which they did. And so I thought they did it. I could be wrong. I think this article could be before Llama 2. Yeah. When and not if open source models reach accuracy levels compared to GPT 3.5, we expect to see a stable diffusion like moment for text, including massive experimentation, sharing, productionizing of fine-tuned models, etc. The hosting companies like Replicate are already adding tooling to make these models easier for software developers to consume. There's a growing belief among developers that smaller fine-tuned models can reach the state-of-the-art accuracy in narrow use cases. 100%. I mean, I recently saw a meme where it was like, I think Starship Troopers, and there's this big brain bug which is OpenAI's GPT, and there's like, oh, it's afraid with the script kiddie running, Llama 2 on this, and I run Olama locally, and it's brilliant. I mean, you can get these quantized models, and they are good enough for most cases, right? So most developers we spoke haven't gone deep on operational tooling for LLMs yet. Caching is a relatively common, usually based on Redis, because it provides application response times and cost. Toolings like weights and biases and MLflow, ported from traditional machine learning, or prompt layer and Helicon, purpose-built for LLMs, are also fairly widely used. They can log, track, and evaluate LLM outputs, usually for the purpose of improving prompt construction, tuning pipelines, selecting models, etc. There are also a number of new tools being developed to validate LLM outputs. Example, guardrails are detecting prompt injection attacks. Example, rebuff. Most of these operational tools encourage use of their own Python clients to make LLM calls. So it will be interesting to see how these solutions can coexist over time. Yeah, I mean, there's my colleague was asking me, how do you unit test LLM apps? And I think essentially you have to fall back on embedding databases, send it out to a smaller model to extract text from the output to make sure that the intent is covered. So that'll be pretty interesting to see how you can productionize and increase quality for these sort of like LLM apps. Finally, the static portions of LLM apps, that is everything that other than the model is also needed to be hosted somewhere. The most common solutions we have seen are standard options like Vercel and major cloud providers. However, two new categories are emerging. Startups like Steamship provide end-to-end hosting for LLM apps, including orchestration for Langchain, multi-tenant data context, async tasks, vector storage, and key management. And companies like Anyscale and Modal allow developers to host models and Python code in one place. Yes, I believe. I mean, you have the bigger guys who are going to win. I mean, like Vercel is there because I mean, it's easy. I mean, it's kind of like most of the apps are built with Next.js, and Langchain also has this JavaScript component. I think the community which is building on Langchain JS and with OpenAI JavaScript bindings is essentially on Vercel, and the others are essentially like Modal, Streamlit, are all on like Python. So I think they're going to use those cases. So I think it's also the choice of like your programming language or your tooling that you're comfortable with is essentially dictating these. But I mean, there's nothing which, I mean, if you're already hosting your apps on AWS or GCP or what have you, it just makes sense to just, I mean, these are just normal apps. So you could just use ECS or Kubernetes or whatever that is to orchestrate your workloads. What about agents? The most important component missing from this reference architecture are AI agent frameworks like AutoGPT, described as an experimental open source attempt to make GPT-4 fully autonomous. It was the fastest growing GitHub repository this spring, and practically every AI project or startup out there today includes agents in some form. Most developers we speak are incredibly excited about the potential of agents. The in-context learning pattern we describe in this post is effective at solving hallucination and data freshness problems in order to better support content generation tasks. Agents, on the other hand, give AI apps a fundamentally new set of capabilities to solve complex problems, to act on the outside world, and to learn from experience post-deployment. They do this through a combination of advanced reasoning planning, tool usage, memory, recursion, and self-reflection. So agents have a potential to become a central piece of an LLM app architecture, or even take over the whole stack if you believe in recursive self-improvement. And existing frameworks like Langchain have incorporated some agent concepts already. Yeah, I mean, you could declare tools in Langchain and have that use. Um, and I mean, we built a chatbot for as a POC, and I mean, it's pretty cool. I mean, you can they already display agent-like behavior. So there's only one problem: agents don't really work yet. Most agent frameworks today are proof of concept phase, capable of incredible demos but not reliable, reproducible task completion. 100%. I mean, we also found that you have to be very specific on the kind of prompts that you want to ask for it to trigger the tool agent. So yeah, but and this is where I feel prompt engineering will play a role. I feel well crafted prompts, before and after the user input, would essentially guard against most of these problems, but they're also easy to jailbreak, right? So we'll need to be careful about this. We are keeping an eye on how they develop in the near future. So, looking ahead, pre-trained AI models represent the most important architectural change in software since the internet. They make it possible for individual developers to build incredible AI apps in a matter of days that surpass supervised machine learning projects that took big teams months to build. The tools and patterns we've laid out here are likely a starting point and not the end state for integrating LLMs. We'll update this as major changes take place, example, a shift towards model training, and release new reference architectures when it makes sense. Please reach out if you have any feedback on session. This is a great article. I can't wait to dive into Vivery, and as I do, I'll be sharing more insights and updates on both LinkedIn and YouTube. To stay in the loop, go ahead and follow me on LinkedIn. And if you're tuning in via YouTube, don't forget to hit that like button and subscribe to my channel for more videos on AI, software engineering, and leadership in the tech industry.